All right, today we're taking a look at alternating series. So we need a definition of what this means first. So if a sub n is positive, then the alternating series is defined as being n equal 1 to infinity, the summation of n equal 1 to infinity, of negative 1 to the n times a sub n, or you can have it be n plus 1 for that exponent. They're interchangeable. These converge when, number one, the limit as n goes to infinity of a sub n is 0. Okay, so once again, you see that sequencing limit going to 0. And number two, a sub n plus 1 is less than or equal to a sub n for all n. That's the same thing as saying that the terms are decreasing as we go, or potentially staying constant, but that's what we're looking for. And if these conditions are not met, then the series will diverge. If one or the other is not met, it diverges. So when we're dealing with alternating series, one of the things that we try to do in general with series is just look at the sequence part. And when we look at the sequence part going to 0, we want to say it works and it goes to 0. And sometimes we find that it can't, like in the harmonic series or in the p-series test and some of those, right? And so when we have an alternating series, that's actually a true statement, okay? We've got to have the decreasing thing, and that's got to be working for us. But the fact that the limit goes to 0 really means something now, again, whereas before it doesn't necessarily mean that it converges. So we're going to determine with the first two questions here whether the series converges or diverges. So the first one is the summation from n equal 1 to infinity. It's got that form, negative 1 to the n, and then we have the n squared over n plus 1 in it, right? And we have two conditions that we have to check. We have to check, number one, that the limit goes to 0. And if it fails, then we're done and it diverges. And then number two, if that succeeds and it goes to 0, we have to check and make sure that we have a decreasing sequence. So we're going to start with the first one. Hang on. So the first thing to check is that the limit of a sub n, which is the part that doesn't have the negative 1 to the n, so this part, we want to know what happens as this goes to infinity. Okay, we've done a number of ones like these. What would you do to show this?
What are you saying what to do next?
Yes, what's our next step?
Hospital's rule.
You could do L'Hopital's rule, that's an option. Can you tell, just based on this, what we expect to have happen? What do you expect to happen here? It goes to infinity. How do you expect that? I mean, like, why do you expect that?
Power of exponents.
The power is larger on top, right? Yeah, the power is larger on top. So L'Hopital's rule would be fine, and since that's the one you mentioned, that's the one I'll use. You can also multiply by 1 over n or 1 over n squared, either of those options, and look at the ratios for that if you wanted to as well. So those are a couple different ways. So I'm going to put an L in here to remind us that that's what we did. So if we use L'Hopital's rule, we would have 2n over 1, right? And this actually tends to infinity. And although it's obvious, having to state it, that's not 0. So what does that mean?
Divergence.
It diverges. And this will diverge. Why?
The alternating series.
Yep.
Test.
By the alternating series test, because the limit as n goes to infinity, goodness, let's try that again, in infinity of a sub n does not equal 0. Right? That's what the alternating series says. Since that limit does not equal 0, the whole series is going to diverge. So, you kind of like it when it diverges because the problem ends quicker, right? There's no second thing to check. If it fails the first condition, that's great. That's the one we want it to fail, okay? All right, let's try another one. Let's see. So on this one, we still have an alternating series, or have another alternating series, that negative 1 to the n part. And we have 2e to the negative n for our a sub n part. So our first step is to prove or to determine what happens if the limit as n goes to infinity of 2e to the negative n. Caleb, I think this is almost the same one you were just asking about, isn't it?
Yeah.
Yeah. So Caleb was asking about that e to the negative n part, and it's showing up in this problem. So it might be more helpful on this to actually write this in a form like this instead. All right, do you remember what the graph of e to the n or e to the x looks like? Yes, this knows. I'll sketch it in real quick too, so we have it written for us. So this is just e to the x. And it looks like this, right? Crosses at 1 on the y-axis. That's more or less the graph of it. What is it doing as n or x goes to infinity? It's going to infinity. And what happens when we have the limit of 2 over something that's becoming infinitely large?
Versus 0.
That's 0. So this is 0. Okay. Second step, to determine that it's decreasing. You can justify this in language, you can justify it with graphs, you can write it out with a sub n plus 1 and a sub n's, whatever you'd like. I don't have it written out in my notes with the a sub n's, I have it more justified in language. So I think I'll just stick with that so that I don't lead us astray on something, but I think any of them are actually not too bad to do if we were to put in the n plus 1 there, because we're dealing with exponentials, they'd collapse pretty easily in my imagination, that's what's happening. So why is this a decreasing sequence? That is the 2 over e to the n.
This is n gets larger,
What happens as n gets larger? Go ahead.
the number underneath the denominator will increase, which makes the number smaller.
Correct. So as n goes to the infinity, e to the n, actually I'm going to write it the way you just said it, increases. Or is increasing, might sound a little better. So 2 over e to the n is decreasing. Okay, everybody good with that? Okay, that's condition 1. Condition 2, so what does it mean?
Convergence?
Yes, so our series converges. Why?
The alternating series.
Yes, by the alternating series test. Remember, be in the habit of telling me how you know. Right now it's obvious, it's the only test in the section, I got that. But in general, we're very, very quickly ending that. We're going to be in a place where we have to know what we're working with in general, okay? Okay, some series don't alternate exactly, but they do have some positive and some negative terms. So sometimes a series may have with positive and negative terms but not be alternating. For example, sine. Summation from n equal 1 to infinity of sine of n over n squared. You have sine of 1 over 1 plus sine of 2 over 4 plus sine of 3 over 9 and so forth. Because sine oscillates, right? Sometimes it's positive, sometimes it's negative. So it has both positive and negative terms. But it doesn't alternate because of pi, right? Its period is pi and 2 pi, depending on where you're, like it doesn't work around the integers, which are what we're working with when we're working with sequences, n equal 1, 2, 3, 4. So it's not alternating. But one way to gain some information is to consider the summation from n equal 1 to infinity of the absolute value of sine of n over n squared. If we think about our direct comparison test, which you've just come off of homework on, right? Direct comparison test. The absolute value of sine of n over n squared is less than or equal to 1 over n squared. And by p-series, we know that the summation from n equal 1 to infinity of 1 over n squared converges. So that must mean that the summation from n equal 1 to infinity of the sine of n over n squared's absolute value also converges. Now, that doesn't tell us exactly what we wanted to know about sine n over n squared, but it's a similar thing, right? It's just in absolute values. So when something converges, when you put the absolute values around it, we actually have some verbiage for that, some vocabulary. We call that, I'm not there yet, Theorem 916 first. Okay, Theorem 916. So when this absolute value of A sub n converges, this series, the series itself actually also converges. In other words, the signs did not make it not diverge. The fact that some of those signs were negative doesn't have a lasting effect on the convergence of the series. But we do have some language associated with what happens when this converges versus what happens when it doesn't. So when the absolute value one converges, right, at the very end of this is definition number 1, when the summation from n equal 1 to infinity of the absolute value of A sub n converges, we call this absolutely convergent. Right? Absolute values, absolutely convergent. But occasionally we find that the summation from n equal 1 to infinity of the absolute value will diverge. Right here, this one will diverge. But the actual function actually converges. And an example of that would be, a real quick, easy example, would be if we did the summation from n equal 1 to infinity of negative 1 to the n of 1 over n. If I take the absolute value of this thing, the negative 1 over n, negative 1 to the n doesn't matter, right? I would just have 1 over n. What do you know about the summation of 1 over n? It's a very special one that we've talked about.
It's a harmonic.
It's harmonic, and what happens in the harmonic series? It diverges. So if I put absolute values around this thing, right? Let me copy it, actually. If I put some absolute values here, the sucker would diverge because it would actually turn into the harmonic series, which we know diverges. But this doesn't diverge. How do you know, or how do I know? Why can I say for sure this doesn't diverge? Yeah, it passes the alternating series test on the previous page. The limit's 0. It's alternating first, right? The limit's 0, and it's decreasing. So in this case, even though the absolute value doesn't doesn't converge, the original function itself does. So that's what we would call conditionally convergent. Okay? So if it's absolutely convergent, we get convergent for free. But just because it's not absolutely convergent doesn't mean it doesn't converge at all. It just means that if it does, it's a conditional statement. It's a sometimes thing. So let's do an example. Full out instead of just me throwing one in there. So this is the summation from n equal 1 to infinity of negative 1 to the n plus 1 over n squared. That's probably worth pointing out that when we originally defined this, we said we could have it negative 1 to the n or negative 1 to the n plus 1. It just changes which terms are positive and negative, right? So whether it has an n or an n plus 1 means either the even terms are negative and the odd terms are positive, or it flips it. So that's why it doesn't matter that that piece has an n or an n plus 1. So what we're going to do is we're going to take a look at the absolute value to start with. So we're going to take the summation from n equal 1 to infinity of negative 1 to the n plus 1 over n squared and take the absolute value of that. So when we do that, all it does is to remove the negative 1 part, yeah? Okay, what do you know about this series?
Converges.
It does.
By P-series.
That'll work. Okay, so this converges by p-series. All right, so when the absolute value one converges, that's our best bet because that's the least amount of work. If it converges right here, it means I'm done. What does it mean about the original series? Converges Absolutely, exactly. So the summation from n equal 1 to infinity of negative 1 to the n plus 1 over n squared converges. Absolutely. Okay, and that's a definition, so I don't need to say, there's not a justification in terms of a test. That's the definition. So if you wanted to say by definition, you could do that. Okay, I've got a couple more. Okay, so we're going to do one that has a log in it. Remember our favorites, of course. So if I do the summation from n equal 1 to infinity, the absolute value of negative 1 to the n plus 1, oops, over n natural log n, we'll get everything but the negative 1 part of it, right? N, ln n. Now what? So we're going to use the integral test. I'll write mine to the side. So what will, before I get there, we'll have 1 over x ln x dx. What will we do to integrate this?
U equals ln x.
Good. So u equals ln x du equals 1 over x dx. So we can change this to being the integral of 1 over u du, which is natural log of u, right? I left off my limits of integration. This is 1 to infinity. I'll leave them off there at the end, and then this is the limit as n goes, not n, we'll use b. B goes to infinity. It's a natural log of u, but then I need to let my u be replaced by what it's equal to, which would be another natural log of x. There we go. And it's from b to 1. So what is the limit?
Is it not the 2?
Did I mess it up?
On my paper it says 2 instead of 1.
Oh, it's a typo on my screen, but it's on the paper, right? You're right. This should have said 2. It needs to be a 2. Otherwise it doesn't work. Thank you. There we go. B to infinity of the natural log of the natural log of b minus the natural log of the natural log of 2. Okay, so what is this limit? What is the natural log of the natural log of b as b goes to infinity?
Infinity.
Yeah, this piece right here is infinity. This piece is a number, right? It is a number. But when I take infinity and subtract off any number, I'm still getting something that's infinite. So what does that mean? Did a great integral in the middle of all this.
The absolute value diverges.
Okay, so the one that I've been working on diverges. Why does it diverge, Robert?
Because of the integral test.
Yes, it diverges by the integral test. Diverges by the integral test. Now, that's not the best news ever, because it doesn't necessarily mean that the original one converges or diverges. It puts us back into the category of, now I don't know which one it is. Are you with me? Okay. So now we've got to go back and see what happens when the negative 1 is a part of it. Well, if the negative 1 is a part of it, what test am I going to end up using?
The first one we did today.
The first one we did today,
Alternating.
alternating series test, right? So we're bumped back to what we did at the very beginning, all right, to the alternating series test. Notice, starting with the alternating series test is not a good place to start here, though, because in order to start here, it wouldn't help me. Like, if that ended up being divergent, then that would be helpful. but it still wouldn't tell me what happened about the absolute value, right? So either way, you stand a chance at having to do the other step. There's not like one that's going to be better for you to start with than the other one. So we tend to start with the absolute value one first as our first step, okay? So, which is what we did. So back to the alternating series test. I don't have that written down there like that. Yeah, I left that part off my page. Oh, no, I didn't. There it is. Okay, so it doesn't converge absolutely. So our original sequence, summation from n equal 2 to infinity of negative 1 to the n plus 1 over n ln n does not converge absolutely. I mean, that's what we've shown so far. So we got to see if it converges conditionally. So by the alternating series test, we can look at the limit of just the sequence. So as n goes to infinity, the sequence of negative 1 to the n plus 1 over n ln n, which would be the limit without the negative 1 part, right? All right, so what happens to this? What is the limit as n goes to infinity of 1 over n ln n?
0.
It's 0. Why?
It's a constant over infinity.
Yeah, because this value n ln n, right, goes to infinity. That's why. The denominator is going to infinity. You've got a constant in the numerator, as you pointed out. Thus, the series from n equal 1 to infinity of negative 1 to the n plus 1 over n ln n converges how?
Conditional.
Conditionally. Or you could say is conditionally convergent.
So do we not have to show that it's decreasing?
Oh, we didn't do that step. We didn't write it in. We do need to do that, yes. We did one step here. So this was 1. Why is it going to be decreasing?
If it's this.
The same thing on the bottom, yeah. And it's decreasing for the same reason. Sorry, I just failed to write that. It's also decreasing for the same reason. The denominator is increasing, therefore the whole fraction is decreasing.
For the alternating series test, do we
Mhm.
have to put the absolute value in there, or can we just go straight to?
You can start the second step if you'd like to. I'm okay with that. I wanted you to see why it's disappearing. It's
Okay.
disappearing because of the absolute values. But yes, if you were to take it off, you could do that. And to be honest, at this point as well, it's not even needed right here, right? That's not what I meant to do. So I meant to do these steps right here. These two absolute values aren't really necessary at this point since I've already taken the absolute values. So you could leave those off as well.
Yeah.
Yes, you could do that. Okay, I have one more example. Are we good to continue? Okay. I'm missing a parenthesis on the screen. Let's put it in there. All right, we have an alternating series, correct? And we're trying to decide if it's absolutely or conditionally convergent, or perhaps if it just diverges altogether. So let's take a look at the absolute part first. So if we look at the summation from n equal 1 to infinity, just down here a little bit, of negative 1 to the n plus 1 of 2n plus 3 over n plus 10 absolute value. So we're starting with this. We're starting by looking at the absolute convergence. That's what we're looking at. That's where we start. Okay, and just like Caleb said, if you wanted to leave this and just move on to the next step, you could do that without this step there written. N equal 1 to infinity of 2n plus 3 over n plus 10. Okay. Now what?
Take the limit.
Okay. What would we be shooting for by taking the limit? It's a good approach, but why is it going to be helpful for us right now?
See if it, you could use the limit test to see if it converges or diverges.
Okay. So the limit test doesn't work here. It works if it's an alternating series, which we'll do it in the second part if we need it.
Okay.
There's another reason why taking the limit would actually be helpful in this particular one. Do you know, Maggie?
Is it the interim test?
This is the nth term test. Take a look at that ratio of the numerator and the denominator. What is the limit? 2. So the limit of this sequence, 2n plus 3 over n plus 10, is 2. And the nth term test for divergence here is actually helpful. Now, if this limit had been 0, it would not have been helpful here, right? But because the limit's not 0, finding the limit's actually a very helpful step. So we're going to take the limit as n goes to infinity of 2n plus 3 over n plus 10, and it's equal to 2, right? We'll be a little clearer. You can do L'Hopital's if you want to, or you can multiply by the 1 over n. Which space do I have? Barely. Okay, so this limit's 2. So what does that tell you?
So divergence for this part.
Yeah, so this part, which is the summation of the absolute value of negative 1 to the n plus 1 times 2n plus 3 over n plus 10. No, I shouldn't even put that part. Let me take this part out. It was just the 2n plus 3 that we were looking at so far right now. Okay, this part from n equal 1 to infinity diverges by the nth term test for divergence. Sometimes it's also just called the divergence test. So by the divergence test, this will diverge. So the series that we started out with, n equal 1 to infinity of negative 1 to the n plus 1 times 2n plus, I'm out of space, let me move down. All right, here we go, 2n plus 3 over n plus 10. This does not converge absolutely, right? Notice my absolute values are not around that, but it does not converge absolutely. Okay, so it's not absolutely convergent, but it could still be conditionally convergent, so it kicks us back to the alternating series test now, right? So alternating series test. So what does the alternating series test tell us to do? Well, there's 2 things we have to check, right? Well, first we need to make sure we have an alternating series, but we have one, yeah? Got the negative 1 to the n plus 1, so we have an alternating series. So we need to check, first of all, the limit part. So the limit is n goes to infinity of the absolute value of negative 1 to the n plus 1 times 2n plus 3 over n plus 10. Or you can write it as limit as n goes to infinity of everything without the negative 1, 2n plus 3 over n plus 10, which looks suspiciously like something we already did above, doesn't it? It doesn't always happen that we end up in the same boat that we were before, but we did here. What is this limit? 2, right? See above if you want. We don't need to rewrite it again. We already did it. This is 2. So what does that tell you?
Divergent,
Yeah, by,
AST.
yeah, so by the alternating series test, AST, the summation from n equal 1 to infinity of negative 1 to the n plus 1 times 2n plus 3 over n plus 10 diverges. Okay, so we saw one of each case, right? We saw one where we have it converging absolutely, and boy, is it friendly when that happens. That is the easiest scenario. We saw one where it converges conditionally. It's a lot of work. Depends on the problem how much. And we saw one where it diverges, and it's also a lot of work when it diverges completely. Yeah.
At the end of that last one, did you explain how it was decreasing?
You don't need to because it failed condition number 1.
Oh, okay.
It wouldn't even necessarily be decreasing,
Okay, sweet.
and so it doesn't matter. Yep. Yep.
Wouldn't you want to start with figuring out whether it diverges and then go and find absolute convergence? 'Cause
Yeah,
then that just saves you a
so-
step.
So if you know for sure that it's going to diverge, like on this one, then that would be easier, wouldn't it? Because we would save ourselves the step in between. But take a look on this one. On this one, proving that it converges here at the bottom means I'm still going to have to go back up to decide if it converges there. And then over here, converging in the bottom, again, I still have to go back up. So in 2 of the 3 cases, because there's basically 3 cases, it doesn't save you any time. It just depends on the series. Now, if you happen to notice, though, Caleb, like let's say, for instance, you're looking at this one to start with, and you're sort of thinking about it from both angles. You're like, okay, I've got these 2 things I'm probably going to potentially end up having to do. But I'd kind of like to know if I could avoid having to do one of them. And if you happened to recognize at the very beginning of the problem that this bottom part with the alternating series test was going to happen, could you avoid the part in between? Yes, you could. But you have to be really in tune and aware of what's going on in all the processing to do that. Okay?